So in this example, we're supposed to determine whether the mean value theorem can be applied to each of these functions on its interval. And if it can be applied, then find a value of C. It's the value of C that the mean value theorem guarantees. So the one where the derivative at C is equal to the average rate of change for the function over the given interval. So looking at example A here, f of x equals x minus 5 over 3 plus x. So that function is undefined when x equals -3, right? We've got a problem with the domain at -3. The mean value theorem applies to a particular function when it is continuous and differentiable. And this function is not continuous when x equals -3. And the other thing to notice is that -3 is included in that interval from -4 to 4. So the function is not continuous over that interval, meaning mean value theorem does not apply. And so that's all we would really need to say then. There's no sense in going further with that example. So this next function, f of x equals the square root of x plus 4. That function is continuous for all x greater than or equal to -4, because you'll have 0 in the denominator or in the radicand, 0 under the radical when x equals -4. And if x is anything greater than -4, then we'll have a positive number here. So this function is continuous whenever x plus 4 is greater than or equal to 0. So when x is greater than or equal to -4, which does coincide with that given interval. So the function is continuous on the interval from -4 to 4, and it's differentiable on the open interval. Let me write that down. This is, I'm going to abbreviate differentiable here, on the open interval from -4 to 4. So for example B here, the mean value theorem does apply. And so that means now we should go through the second phase of the problem, which is to find a number C between -4 and 4, such that f prime of C equals the average rate of change over this interval. So I'm going to start by finding the average rate of change. So for this interval, that'll be f of 4 minus f of -4 divided by 4 minus -4. It's our change in y over change in x. F of 4 right here will be the square root of 4 plus 4, so the square root of 8, which can be simplified, but I'm going to just leave it like that for now. F of -4 will be the square root of -4 plus 4, so that's the square root of 0. That's 0. So the numerator here is the square root of 8 minus 0, so it's equal to the square root of 8 over 4 plus 4, so this is over 8. So that's our f of b minus f of a over b minus a part of this. Now f prime at c, well, if f of x is the square root of x plus 4, which can be written as x plus 4 to the 1/2 power, then f prime of x is equal to 1/2 x plus 4. I'm using the chain rule here, so I leave the inside alone. Subtract 1 from the exponent. So now I've differentiated that 1/2 power times the derivative of the inside, which is 1. And so I could rewrite this as 1 over 2, and the square root of x plus 4 will go in the denominator because of that -1/2 power. So here's the derivative. This gives you the instantaneous rate of change. We can now set it equal to the average rate of change and solve for x. This is how we can find the value guaranteed by the mean value theorem. So I could take this, I could multiply both sides by the least common denominator. which would be 8, and 8 will include a factor of 2, so I don't have to list 2 separately, and then the square root of x plus 4. So I'm going to multiply both sides of that equation by 8 square root of x plus 4. So 8 square root of x plus 4. I know this is looking pretty messy here. Maybe I can make this a little better. 8 square root of x plus 4. Okay, I'm going to switch to black. So when I simplify that, I'll have, well, the square root of x plus 4 will cancel here. And then I have 8 divided by 2, so that's 4. And then on this side, the 8's cancel, and we have the square root of 8 times the square root of x plus 4. I could combine those, write it under a single radical if I want to. So we could write it like this. And so now, so we're trying to isolate x. I will square both sides. Square this side, square this side. So that will give me, ooh, I'm having trouble changing colors. 4 squared, which is 16, and then squaring this radical, so you end up with just what's underneath. And now divide both sides by 8, and then subtract 4. So this gives us 2 equals x plus 4. So if you subtract 4, negative 2 equals x. Whoa, 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 whoa. Wait. Sorry, my little writing tool went wild. So when x equals negative 2, this is, it is a value between negative 4 and 4. This is where the instantaneous rate of change is going to equal the average rate of change. As a quick illustration, I'll try to make this quick. 1, 2, 3, 4. So the graph of f of x equals x plus 4 would go through negative 4, 0. And then what other numbers are nice to plug in? If x is negative 3, then y will be 1. If x is 0, y will be 2. Okay, so the graph of that square root function looks something like this. At 4, we get square root of 8, which is what, 2 times the square root of 2. So it's around 3. Okay, what I want to draw is the secant line through these endpoints, negative 4 and 4. So the secant line looks something like this. And if you picture the tangent line at negative 2, so that's right here, it does look like, I mean, it's believable anyway, that the tangent line would be parallel to, the tangent line at negative 2, I should say, would be parallel to the secant line through those two endpoints, which is one way to interpret the mean value theorem. Okay, so that's example B. Let me see if I can include in this video a solution to example C. So I'm going to erase a lot of this, which is not going to go as fast as I wish. Let me go ahead and talk about that example C there. So now we're looking at the function f of x equals 8 times sine of x. The sine function, cosine functions, those are continuous everywhere. They're nice like polynomials. So that function will be continuous and differentiable on the interval from 0 to pi. And in fact, it's continuous and differentiable over any interval. So mean value theorem does apply to example C as well. So that means that we should find this, again, solve for x in this equation, or solve for C. I know I solved it in terms of x a minute ago. So we set the instantaneous rate of change, which is equal to the derivative. So in this case, that will be 8 times cosine of x, which is the derivative of sine of x. set it equal to the average rate of change, which is going to be change in y over change in x. So that's f of pi minus f of 0 divided by pi minus 0. So change in x is equal to pi minus 0. F of pi, so that'll be 8 times sine of pi. Well, sine of pi is 0, so this is 0. And sine of 0 is also 0, so 8 sine of 0 is also 0. So this numerator is 0 minus 0, so it's 0. And then 0 over some non-zero number, that's just 0. So we're looking for the solution to this equation that lies in this interval from 0 to pi. If we divide both sides by 8, then we get cosine x equals 0. You could picture the unit circle. Again, we're looking at the interval from 0 to pi. Cosine is associated with the x coordinate when you're reading values off the unit circle. So the x coordinate is 0 here at pi over 2 radians. And so our solution in this case, and I know in the statement of the problem, I call it C, but I keep solving for it in terms of X. But it's just, you're looking for the X value at which the instantaneous rate of change, which is given by the derivative, is equal to the average rate of change. That's the overall idea with these problems. You're guaranteed at least one X value where this happens as long as the function is continuous and differentiable. That's the idea with mean value theorem. So in this first example, it was not continuous on the given interval. These other two did meet the requirements, and we successfully found a value inside each of these intervals where the derivative is equal to the average rate of change.